All right, so now we're going to begin a series of topics where we're going to wander through the subjects that will get us to the notion of the connection. And we've already talked a lot about the connection, so I'm not going to be teaching what the connection is from the start. But what I am going to do is I am going to describe the connection that's used in general relativity. Right? We've talked about the connection in a mathematical sense, and in the sense of differential geometry and some of our work with tensors and manifolds. But what about the connection as far as general relativity goes? How does that apply? And, in general relativity, we have our basic model of space-time, which is a manifold that has coordinates. And I've been writing this for a very long time. And we've already explained that at each point in space-time, we have these tangent spaces. And these tangent spaces contain essentially, the tangent space is a vector space, but associated with it is a covector space, and all of the equivalent tensor product spaces, right? We've still got that going. And we also know that in order to make this space-time, if we call the space-time S, and S is the set of all the points in space-time, and it's a manifold, right? So S is a manifold, and because it's a manifold, we know there's a coordinate system, x0, x1, x2, and x3, and all of those points make up the space-time. But even as a manifold, and even with a coordinate system, right, where we can make patches and lay down coordinates using the charts, right, so I guess you could say that S is a space-time. It's actually a set of points M and an atlas A, right? That's what that's all about, right? The atlas is what gives it the coordinates, and the atlas is the atlas A, of course, is itself a set, right? The atlas A is a set. It's a set of charts let's say U alpha, gamma alpha. And it's the set of all those charts which map every point into R4 in our case, into R4. That's what these little maps do. And so the space-time is that manifold, but it's more, right? The space-time is actually the manifold S and a metric, right? The metric is what makes the difference here, because the metric is what binds together all of the inner products at all of these points. The metric defines an inner product at every point in space-time, which allows you to do things like take two vectors from the underlying tangent space and determine something like a magnitude. It allows you to do all of this measurement. So that's cool. So we know that that's how our model of space-time is going to work. And we know ultimately that the Einstein equation, right, is going to take matter, stick it in there, and then space-time is going to pop out here, and space-time means the metric, right? So that's how you're going to do it. You're going to start with matter, which is all forms of energy. You're going to jam that energy in this part of the right side of the equation, and then the left side of the equation is going to give you your metric. And then these two things together, right? These two things together, the manifold and the metric, that's the arena of general relativity, and that's what the subject really is all about, right? But you may remember when we formulate the laws of physics, we do it with usually differential equations, right? And we've already described in previous lessons on the What is a Tensor series about the connection and how that's related to the covariant derivative, right? So if I have a tensor A, B, I can take its covariant derivative, which frequently is with a semicolon, with respect to space-time indices, or I can or a better notation, the notation I like is with these two lines, right? And we talked about that. But in order to do these covariant derivatives, we need to create the connection. and here's an example of a connection was gamma, right? We called gamma the connection. And the connection and the metric are not the same thing, right? The metric just tells us how to take an inner product at any given point, right? The connection is what tells us how parallelism works, how we can understand a vector in the tangent space here and understand it with a vector that's in the tangent space here. Notice how I draw the vector literally inside the tangent space, where here I drew the vector like attached to the point, and here I drew the vector inside the tangent space. This is the more correct view. This is the one almost every textbook uses. But this is helpful. Once you start understanding as long as you understand this is what's going on, this is fine, because we're always going to talk about very small displacements, and slowly you can kind of blend these two thoughts together. But the point is the connection breaks the seal. I mean, even though you have a metric that tells you what the inner product is at every point in space-time, that doesn't do anything to connect this tensor product space with that tensor product space. This tensor product space, or this vector space, this tangent space, and this tangent space are still an infinite universe apart. They're totally different objects, even though they have a metric which tells me the relationship, or tells me they're two separate inner products. So for example, I can have G alpha beta, if this is the point P, I can evaluate it at the point P. Now when I write this, by the way, what I'm really saying is G alpha beta at the point x mu of P, right? That's how the manifold works. I insert the point there, I get the coordinates there, and G alpha beta is a function of the coordinates, right? So here I have G alpha beta of x mu of the point Q, right? If this is the point Q. And sure, I have a tensor field, a 0-2 tensor field called the metric, and it's a function of the coordinates, and I can use those, and it's a continuous function of the coordinates. It's a beautiful, smooth function of the coordinates, and it tells me the inner product right there. And likewise, this will tell me the inner product right there. But that does not establish any kind of relationship between this tensor product space and that tensor product space. In order to do that, I need a connection. So you can now argue that for a space-time, I need a manifold, I need a metric in order to do general relativity, and I need a connection, right? I need three things. So we're going to start getting to the point, well, we're now going to start working towards the direction of going back to this catalog of space-time, which is sort of our reference book here. And we're looking here at the basic objects of a metric, section 1.3 of the catalog of spacetimes. And the first thing in this list, 1.3.1, is this object here, which is called the Christoffel symbol of the first kind, and 1.3.3 is the Christoffel symbol of the second time. Let's look at that one, because that one has the Christoffel symbol of the second kind has an object on the left that looks like the connection. In fact, it is the connection. And notice how it takes that connection and it defines the connection in terms of the metric. This is the metric. This is the inverse metric, right? Which is simply the inverse. The inverse metric is just two. You take the metric and you raise the indexes with the metric, and you get the inverse metric. Well, the inverse metric is just defined in the obvious way, right? It's defined where G mu nu G mu nu equals 1, right? But more importantly, it takes the derivative of the metric with respect to space-time, where these symbols are partial G rho nu partial x lambda. This thing here, that's what this means. And notice it's just got one comma, which means it's just a regular derivative. It's an ordinary derivative. So I would have written this G rho nu one line lambda like that in my notation. But the point is the connection is given in terms of the metric. So now if we go back to our little thing here, our space-time, if that's what we believe, then the metric is all we need. and I don't need to write this down anymore. So now what we have to understand is, why is it that if we have a space-time, right, if we have a metric, how does that give us a connection, right? How does that give us a connection? What's the relationship? What's the connection, if you will, between the metric and the connection? And this just goes to show finally, the last step is everything that means anything in this level of our understanding, it's all about the metric. No metric, no nothing, is what some famous astrophysicist once said. And it actually was kind of a stumper problem. Apparently Einstein got very hung up on some issues regarding the fundamental nature of the metric early in the development of general relativity. I don't know if he ever resolved the question fully, but other astrophysicists have, and they decided that the issue is different spacetimes with no metric and with ambiguous metrics. How do they relate, right? And the idea is, no, you have to have a metric. And without a metric, this point here and this point here could be an infinity apart if without a metric. With a metric, you know how far apart they are. The fact that the coordinates are adjacent to each other, or the coordinates have similar values, it doesn't mean anything unless you have a metric. And in fact, we already know that it's a bit screwy, because we already know that in special relativity, I could have a point here and a point here, and they're actually 0 apart, right? If they're on a line of 45 degrees, right? Remember this old TR diagram? That sphere, the sphere here and the sphere here, are an infinity apart, or are 0 apart if they're connected by a 45-degree line, because of the Lorentz nature of the metric. But ultimately, those distances, you got to understand them, but there is a way of taking this measurement of distances and using that to tie together the tangent spaces and then understand parallelism. Because remember, that's what this was all about. This was all about taking a vector that was established at one point P and a vector that's established at a point Q, and saying, hey, there's a vector here in this tangent space, the tangent space of Q, of the spacetime, and there's a vector here at the tangent space of P of the spacetime, and this vector here is parallel to that vector there. We can establish parallelism if we have a connection. And now we want to ultimately learn, as the catalog shows, that that connection is related to the metric. And we need to understand why that is. All right, so that's our goal for the next lecture or two, or 3. It's a bit of a complicated subject, and it's really worth digging into because there's a lot of pieces to it. But before we begin, I want to start and have a good, comfortable understanding of the metric a little bit better. I want to be able to understand sort of the classical nature of the metric. When I say classical, I mean classical differential geometry tells us something about the metric, and that tells us a little bit about how we need to think of the metric in terms of general relativity. So let's begin with an elementary discussion of the metric that is relevant to what we've done before. It's going to connect to the conformal coordinates we've done before. So let's begin that. All right, so something that's easy for us to understand is, of course, Euclidean space, right? Euclidean space with Cartesian coordinates, x, let's see, x, I guess y has to go here, and z has to go there, right? X, y, and z. And we know that the metric for Euclidean space is going to always be written as ds squared equals dx squared plus dy squared plus dz squared, where I use this, I'm using this sort of the casual notation of a metric by describing the line element. So here I would say gxx equals 1, gyy equals 1, gzz equals 1, and all of the off-diagonal elements are 0. So we know that that's the metric of our standard geometry of sort of classical Euclidean geometry. So the question we want to understand is I want to kind of exercise the nature of the metric in a very classical sense just to warm us up, and that's going to take this full lesson. So I want to imagine a surface in this three-dimensional space, and I'll just choose a sphere. Sphere is a nice classical simple surface that is often used for this example. And that sphere is a set of points such that x squared plus y squared plus z squared equals equals r squared, where r capital R is the radius of the sphere. And that's a surface. So we understand that this is a two-dimensional surface in or embedded in three-dimensional manifold. So now we know the metric of the underlying three-dimensional manifold. So now we talk about a curve just in the surface. For example, well, we could talk about this curve here, say mostly around the circle, or we could talk about some arbitrary curve on the surface, right? Some curve that kind of goes, connects one pole to the other, but it doesn't have any particular symmetry on the surface, but it is fixed on the surface. And we can calculate the length of these lines, the length of these of those two curves, and they are curves, right? So given the fact that they're curves, what do we remember about curves? We remember that curves, we describe it with a parameter. Say the parameter is tau. Tau might go from 0 to 1, and then the curve itself could be, say, gamma of tau, and it maps into or onto the sphere. Now you can think of it as mapping onto the sphere or into the three-dimensional space, right? Because it is, this curve is in the three-dimensional space. It's just on this sphere. So you can think of it both ways. You're either mapping onto the surface of the manifold or onto the two-dimensional. This is a manifold here. This is a manifold here too. This is a submanifold of this one because it's a manifold embedded in a manifold. The three-dimensional one is very easy. We only need one chart. This one actually you would need two charts. We discussed that in the What is a Manifold lecture series. So you can think of this as going both ways. This could either be a function, this gamma of tau is really gamma 1 of tau, gamma 2 of tau, gamma 3 of tau, where this would actually ultimately be x, y, and z, and in our more standard notation it would be x1, x2, x3, right? Where we could define, we're just naming things the way they're commonly named. So the gamma tau could be right into three-dimensional space. But remember, this is a manifold, right? And as a two-dimensional surface, it has two coordinates, right? And those coordinates could be theta and phi, where those are your standard angular coordinates in of a surface of a sphere, as long as it's all in one chart. And then you could instead consider gamma tau to equal gamma 1 prime of tau and gamma 2 prime of tau. I just need to distinguish it from these guys, right? Who've already claimed the 1 and 2 index. And that would actually be theta of tau and phi of tau, right? I could have written this as x of tau, y of tau, and z of tau. And that would have been x1 prime, comma, x2 prime, right? I'm just using a few different notations here. All of tau. Everything's a function of tau. Everything's a function of the parameter. So there's two ways of doing it. And likewise, I can measure the length of that curve in both coordinate systems. And to measure that length, I'll need the metric. So I could use the metric, let's call the metric of the Euclidean space G Euclidean, or if I'm using this set of coordinates, I could measure that curve using the metric of the sphere, which would be G of the sphere. But what's important and what I want to show today is that this is an easy metric. This metric, not so much, right? I mean, we know what it is, but in principle, we should be able to take an arbitrary surface, not just a nice sphere. We know what it is because we know all about spheres, but it could be any surface. And it seems like if you know this metric here, you should be able to figure out what the metric is on the surface. It means if I know the metric of the underlying space in which this manifold is embedded, right, that's this metric, shouldn't I be able to figure out what that metric is? And yes, the answer is yes, and we are going to do it. But we're going to do it for a case that's a little more complicated than this. We're going to use the four-dimensional sphere. So we're going to exercise thinking in 4 dimensions, and we're going to exercise this thing called the induced metric. The induced metric, which is the metric of a submanifold of a manifold when you know the metric of the embedding manifold. And that's what we're going to do now. Okay, so we're going to begin this by reminding ourselves about the basic sphere, and then we're going to generalize it to one extra dimension. And we're going to play with that for our, it's going to be a sort of an entertaining arena to test our concept of the induced metric. But this sphere is going to be the set of these points that have, let's say, x squared plus y squared plus z squared equals r squared. And that's in 3 dimensions. So this is the set of all points, of all triples, x, y, and z, that satisfy this relationship here. That's the sphere. And then on top of that, we want to create the metric of the sphere. G, let's say, I'll call it G sphere, right? And the metric of the sphere, we want to get that from the metric of Euclidean space. But we also, I want to play more with the more interesting thing is I want to talk about the 4-dimensional sphere, which I don't know quite how to draw it. I mean, we don't need to draw it very much, but if I were to draw it, I kind of draw it the way people try to draw tesseracts, which is one sphere and then a little sphere sort of inside it. And both of these spheres will have, well, first of all, the definition of this thing is x squared plus y squared plus z squared plus w squared equals r, right? R squared. So it's the set of all quadruples, x, y, z, and w, that satisfy this relationship here. And it will also have a metric. I'll call it the glome metric, GG, because a 4-dimensional sphere is often called a glome. But that can be derived from G Euclidean. I'll call it GE4, right? This is G Euclidean from 3 space. This thing is embedded in 4-dimensional space, right? It's embedded in R4. So the metric from R4 should be able to derive the glome exactly the same way the metric from R3 derives the sphere. And in fact, this is the one we're going to do. It's going to take a long time, but we're going to do it. In this drawing that I have, all the points on this sphere have the same x, y, and z coordinates as all the points on this sphere, but they have different w coordinates, right? In some sense, it's like a tessor sphere or something. Don't worry so much about drawing it, because you can't do it. Nobody can draw it. It's just not visualizable, but it is mathematically very clear. So we have the glome and we have the sphere, and I'm going to try to talk a little bit about both in parallel, because this is what's going to give us intuition for this, although it's pretty straightforward. I actually wrote down, I textified, this is my own text, this isn't a book anywhere. This is some text I did to prepare for the optional lecture that was before this about the glome. But you may remember that spherical coordinates can be described like this. The z, y, and x of the Cartesian system can be connected directly to the theta and phi of the spherical system, or r theta and phi of the spherical system, through this coordinate transformation. And so if I establish that the sphere has r equals some fixed value capital R, then this becomes a capital R, a capital R, and a capital R, and this side is two-dimensional, right? So I'm now entering two-dimensional of theta and phi. And so now I have the three dimensions of the R3 space, and now I have the surface of the sphere S on this side. And I can now use, the whole point being that I can use the coordinates on the surface of the sphere to calculate the coordinates in R3 space. That's what this coordinate transformation does. And but it only takes two coordinates to establish any point on the sphere because the sphere is a two-dimensional surface. It's embedded in three-dimensional space, but those dimensions are not all completely independent. They're bound by this expression, right? So you basically lose 1 degree of freedom. So the glome is a three-sphere, and it has the same kind of thing. It has the same kind of coordinate transformation, and that's what these are down here. Now we end up adding an angle variable, very similar to theta. So theta and phi are not the same. They're very different because theta has a range from 0 to pi, whereas phi has a range from 0 to 2 pi. And it turns out that when you go to higher dimensions, and this it's not just the fourth dimension, it could be 6th, 7th, or 8th, or 9th, or 10th dimension. It doesn't really matter. What you end up adding are additional variables similar to theta, but there's only one ever similar to phi. So we start naming the theta type variables, and it's conventional to switch them. I call phi 1, phi 2, and phi 3, etc. for an n-dimensional sphere. Those would all be angles that go from 0 to pi. But lambda would go from 0 to 2 pi. So I kind of changed the notation on between. The reason I'm doing it is this is standard for the paper I learned about n-dimensional spherical coordinates, and this is standard you see in physics books. So anyway, x1 r cosine phi 1. So there's one angular variable phi 1 for the first x coordinate. The second x coordinate would be r cosine phi 2, which is the second angular coordinate, sine phi 1, which is the first. So this is actually a very different kind of thing. It's got two angular coordinates that are in the range from 0 to pi. x3 is sine lambda of sine phi 1 to sine phi 2, and cosine lambda of sine phi 1 and sine phi 2. The last two, this part is the same, but this other angle variable, the one that goes from 0 to 2 pi, makes an appearance. And just as before, if I set r equals to some constant r, obviously little r, as it would be a fourth coordinate, but if I fix it to some value r, then I have reduced this side to an object with 1, 2, 3 coordinates, a three-dimensional object in a four-dimensional space. And that is called the glome. Right? It's really, you can call it depends whether you're a topologist or a geometer, by the way. It's a three-sphere in the sense that it's the surface, its surface takes 3 coordinates. Or it's a four-sphere because it lives in four-dimensional space, right? So it depends on whether you're a topologist or a geometer, and I forget which one calls it which, right? Anyway, so now the question we're going to ask is, what is the metric of the glome? Now we know what this is. We know the coordinate transformation already. Now we're going to ask, what is the metric for the glome? The induced metric from four-dimensional R4, right? We know the metric on R4, right? It's just going to be gxx equals gyy equals gzz equals gww equals 1, right? That's the standard Euclidean metric for R4. Now we want to know what is the metric is on the surface of the glome, which is what is g phi 1 phi 1, g phi 2 phi 2, g lambda lambda, right? Notice there's only, And likewise, maybe there's a G phi 1, phi 2, right? That's not, we know there isn't one here because we know the Euclidean metric of R4. But there could be a cross term here, right? There could be a G lambda phi 1, for example. So we want to do that calculation. And that's the goal of the rest of this lecture. All right, so to begin, we will start by writing down the surface of the globe in very classic vector notation. If I were to write down phi 1, I hope I can stick with these subscripts. I could imagine it getting to be quite a mess, but that's how I did it in the LaTeX, so I should try to stick with it. But if I write this thing down to say, I want to know the point in four-dimensional Euclidean space that is the same as, given these three parameters, right? I want to know the point in four-dimensional Euclidean space. And I want to use sort of this classic vector notation. How would I do that? And I would do that by just writing it out in this fashion. I need a four-dimensional sort of vector object here. I better give myself room. And then I would stick in this stuff right here. I'm going to assume that r is equal to 1. So I'm going to omit these r's for now. So cosine phi 1, cosine phi 2, sine phi 1. So I would write cosine phi 1, cosine phi 2, sine phi 1, and then it would be, I think is it cosine? No, it's sine lambda first and then cosine lambda second with sines. So it would be sine lambda, sine phi 1, sine phi 2, and then cosine lambda, sine phi 1, sine phi 2. And this is just, now we can actually think in terms of vectors, right? Just when I say in terms of vectors, what I should mean is in terms of little pointy things outside in Euclidean space. This is all very basic geometry. So we can lean on all of that classic stuff we learned before I told you to forget it all. However, this is still going to be interpreted as something in the coordinate, this is now a point in, so this is an element of R4, right? And we've implicitly put in an R, an R, an R, and an R here. But I'm thinking that I probably want to choose R equals 1 so I don't have to carry it around. I've already got a problem with these subscripts, right? Because I want to put a comma in here, but the commas will interfere with the 1s and the 2s. So anyway, notation's a big thing for me. I get a little fixated on it. But anyway, so this is a description of the glome in four-dimensional space. And we could likewise have done the same thing for a sphere in three-dimensional space. We wouldn't have this phi 2. We would only have phi 1 and lambda, and then this would be the same. It would be phi 1. This would be gone, and these two would be here, but these two, the sine phi 2s would be gone, but this would be the same. So for regular three-dimensional space, you have this term, and then you have this. And the four-dimensional adds are this guy here, which is unique, which is something you might not have anticipated. And then you have, of course, the additional angle variable there. Okay. So that is the surface that is our glome surface. So with that, I can now map in space this glomey object, which I can't really draw, but it's always fun to pretend that I can think in 4 dimensions. So now my question is, all right, so I'm going to be dealing with things in the surface of this object, and I'm looking for the induced metric. So it stands to reason that I'd be interested in the tangent spaces of the glome, which in regular, if it was a regular sphere in three-dimensional space, I'd be curious about, if I take one point, I want to know about this tangent plane to that point, right? I want to know, every point will have a tangent plane, a plane of tangency between that point and the sphere. And I'd like to know about some basis vectors that cover that tangent plane. In other words, I want to create the basis vectors that point into this tangent plane and cover the whole plane. And I want to know this in the underlying four-dimensional space, right? I want to find the basis vectors in four-dimensional space for the tangent plane of any point on the sphere. Likewise, for the glome, I want to find the same thing, but each point has a tangent space, right? A three-dimensional tangent space. And I want to know three vectors that cover that tangent space for every point on the glome. So how do we do this? Well, we're going to, by analogy, we're going to do this for the three-dimensional case, for the four-dimensional case, or for the glome, the way we would do it for the sphere. And we're going to construct three vectors. I'll call it E phi 1. We're going to create E phi 2. And we're going to create E lambda. And these three vectors are going to be basis vectors for the tangent space at the point phi 1, phi 2, and lambda. And we're going to construct them from this. And the definition for that construction is the same as it would have been for the sphere. It's going to be E phi 1. These are vectors, so I should give them little vector symbols because I can't do boldface on this whiteboard very easily. So E phi 1 is going to be defined as the partial derivative of r, which is a function, I guess I'll make it explicit, of phi 1, phi 2, and lambda, with respect to phi 1. And this is a vector derivative we're taking, so of course it goes into components. This guy here is simply that, right? So I'm going to write, how would I do this? I would say, I would call this, remember, we're dealing with x, y, z, and w, I guess. So I would say it's going to be the partial derivative of x, phi 1, phi 2, lambda, with respect to phi 1. The partial derivative of y, phi 1, phi 2, of lambda, with respect to phi 2. Partial derivative of z, phi 1, phi 2, and lambda, with respect to sorry, I'm confusing myself. This is all with respect to phi 1, right? Phi 1. Z with respect to phi 1. The partial derivative of w, phi 1, phi 2, and lambda with respect to phi 1. Okay, so let me fix this. So that is this vector. So this vector is given by this column vector here. Sorry, changing my symbols here. Of all of these pieces developed through this derivative. Now, x, this is x, right? So I'm using a shorthand where this is x of phi 1, phi 2, and lambda. Now, obviously, x is only a function of phi 1, but in principle, it could be a function of all. This one is y, phi 1, phi 2, lambda. Likewise, z, likewise, w. And I'm dragging around. I think it's worthwhile to drag these around. You know, in any reasonable textbook, it would have just done partial x, partial phi 1, partial y, partial phi 1, because they would assume that you know. But I actually think it's worth dragging it around a little bit. But now, to make connection with what we have done, this could also be better interpreted and probably is more correct. Well, it's a little more error-free if you write this as partial x, partial phi 1, then I'll write x, I'll write phi 1, phi 2, lambda, times the basis vector in the Euclidean space, which in the coordinate basis is going to be partial x, right? And then that will be plus partial y, partial phi 1. Now I will drop, I'm getting sick of them already, I will drop the arguments, partial y plus partial z, partial phi 1 of partial z plus partial w, partial phi 1, partial w. And now these are the basis vectors of the tangent space in the coordinate basis system, right? And this expression here is essentially this. Here it's organized spatially in a matrix form. Here I explicitly take the matrix vectors and pull them out. And this is the preferred way to think about it. This is the sort of the common classical method of thinking about it. Okay, so, but from all that, I have now created, right, I've now created one of the basis vectors of the tangent plane, right? One of the basis vectors of the tangent plane. And I'm looking for all three, right? But the other ones are pretty simple, right? The other one, let's see, I'll go to red here. I just turn that to a 2, and then I'll go to blue here, and this becomes a 2, 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 and a 2, and a 2, and a 2, and we're done, right? That's the value for phi 2. For lambda, because the way I've named these things, because I've pulled lambda out, because lambda is an angle variable, but it behaves differently than phi 1, phi 2. It has a different range. It goes from 0 to 2 pi. And it shows up only in the last two of the transformation. It doesn't show up in the first two. And if this was n-dimensional, it would still only show up in the last two. It's very interesting. By the way, I did an optional lecture on the glome where I literally derived this, where I proved that this was true. So I'm not pulling it totally out of thin air. I actually derived it in the optional lecture called the glome. And it's interesting because you can see how this angle element evolves in that case. So here I would have to now go lambda, lambda, lambda. Well, maybe I should just erase these things here. And this would become lambda. Oops. This would become lambda, 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 lambda. And likewise over here, these guys would all become lambdas. Lambda, lambda, lambda. And then this would be, of course, lambda 2. So we can create all three of these basis vectors by taking this prescription of derivatives. So let's actually do that. Let's actually do that for the glome. So I'll go back to this page here. I'll move that over to there. Let's see, wait a minute. See if I can make more room somehow. Hold on a second. Let's do this. Let's go here and then erase everything. So with these coordinates, let's calculate E of phi 1. That should be pretty easy. It should be the derivative of that with respect to 1, it's going to be minus r sine phi 1, and then it's going to be r cosine phi 2 cosine phi 1, and then it's going to be r sine lambda cosine phi 1 sine phi 2, and then minus, no minus sign. It's going to be r, these should be capital R's, r cosine lambda cosine phi 1 sine phi 2. Sine phi 2. This would be phi 2. And there you have the first basis vector of the glome. And we could do the same for the second basis vector. We could write E phi 2 equals, and let's see, this, going back to this guy, well, that's 0. And then this will be R minus R sine phi 2 sine phi 1. And then this will be R sine lambda sine phi 1. And then I guess it's cosine phi 2. And then this will be R cosine lambda sine phi 1 cosine phi 2. Yeah, and that's this guy, right? And we can think of this as the sum, as this in the sum form, right? Just like I did here, right? We would break it out by, making this guy up here equal to minus R sine phi 1 partial phi, oops, not phi, other coordinates, the basis in the Euclidean system. Remember, this is in the Euclidean system. It's a function of the parameter of the surface, right? The surface coordinates, but the vector is in four-dimensional Euclidean space, and so it has the coordinate basis of the four-dimensional Euclidean space. So I'm saying if given, phi 1, phi 2, and lambda, I'll tell you the vector in four-dimensional Euclidean space that's tangent to the glome at that point. Okay, so it's that, and then it would be plus R cosine phi 2 cosine phi 1 partial y plus R sine lambda cosine phi 1 sine phi 2 partial z plus R cosine lambda cosine phi 1 sine phi 2. Do I have that right? Oh, yeah, okay. And this is partial w, right? So these are two equivalent ways of doing it. Just because it's easier for me to do the calculation, I'll just assume that you're doing this in your head, right? So here's for phi 2, and then for E of lambda, that's real easy. Everything is 0 except these last two, right? And that will be true for any number of dimensions, by the way, because, like I said, for any number of dimensions, lambda only shows up in the last two. I think I have that formula here. Yeah, see, remember, I did this in the other glome lecture, but for n dimensions, this is the general expression. You can calculate this general expression in n dimensions, and you'll see for the first dimension, you always get that. For the next I dimensions, you get these cosines and sines together, but for the last two, that's when you get the lambdas to pop in. Okay. But anyway, E lambda will be 0, 0, and then it will be R cosine lambda sine phi 1 sine phi 2, and then minus R sine lambda sine phi 1 sine phi 2, like that. Okay? So that's it. We've just calculated the three basis vectors in the Euclidean space given any point in the glome's own coordinates. Great. So what next? I should be a little bit more precise here, and now's the time. So we're dealing with these vectors in four-dimensional space, the coordinate vectors in four-dimensional space, but I've got these E1, E2, and E phi 1, E phi 2, and E lambda objects as well. And I want to make it real clear what the connection is, or I don't know about clear, but I want to make sure we struggle with what that connection is. So if we live out in the four-dimensional space and we're looking in at the glome, right? Or likewise, you might be able to think if we're living in three-dimensional space and we're looking at the sphere equivalently, and we use the XYZ coordinate system. This is how we refer to all the tangent spaces at every point. We use this coordinate system, this coordinate basis. So any point in our four-dimensional world, we have access to these four basis vectors. Now it turns out that when we stare at the sphere, however, we kind of realize, we don't actually need all four of these, because at any given point, well, we need all four in some sense, but if I stare at one point on the sphere, one point given by phi 1, phi 2, and lambda, then I don't actually need all four. I can find a linear combination of these four, or I can find three linear combinations of these four, e phi 1, e phi 2, and e phi 3, and every vector in that plane, in that tangent plane, can be expressed with this basis. So I can actually drop a basis, I can drop a dimension by taking the appropriate linear combination of these four and calling that the three basis vectors. Now that's a little bit annoying because I get outside of my coordinate basis system. I'm no longer in the XYZW coordinate basis system. On the other hand, if I actually lived inside the sphere, if I lived inside the glome, I would have my coordinate system is phi 1, phi 2, and lambda. And in that sense, my fundamental coordinate system is going to be partial phi 1, partial phi 2, and partial lambda. And it's only three-dimensional. It's not four-dimensional. And these guys, this partial phi 1, partial phi 2, and partial phi lambda, are connected to these guys through this relationship. E phi 2 and E lambda. Right? So my coordinate basis vectors, or the in-glome coordinate basis vectors, are in fact what these guys are. Right? So any vector in glome that I would write down, some vector x, is always going to be x alpha, or x, I guess I have to stick with the coordinate symbols now, x phi 1 partial phi 1 plus x phi 2 partial phi 2 plus x lambda partial lambda. Now, in general relativity, of course, we would rename this, phi 1 would be likely x, phi 1 would be x1 prime, phi 2 would be x2 prime, phi 3 would be x3 prime, and I would write the vector x to be x mu prime partial mu prime, like that. And that would be the in-glome coordinates. And the out-of-glome coordinates would be x equals x mu phi mu, perhaps. Two different coordinate systems here. In fact, in this case, in order to keep the four-dimensionality, I'd probably have to keep r as a coordinate, right? Otherwise, this would only have 3, and this would have 4. But the point is that naming the coordinates independently is a convenience for this kind of analysis and study. When you start talking about this kind of analysis and study, you actually kind of want to just use a generic coordinate, x1, x2, x3, and then start priming them or giving some other change that will signify that you're in a different coordinate system. But the point is that the coordinate basis in glome is related to the coordinate basis out of glome by this relationship, which you could invert, by the way. You can invert it, but if you inverted it, you could still only capture the subspaces that are on the glome. Okay, so with that in mind, what next? Well, next we are going to work on this induced metric finally. So the point is now, and I'll use the sphere as our example, if I'm dealing with vectors in the tangent plane of a sphere, and I call one of those vectors x and one of those vectors y, then I have, in principle, two ways of calculating the inner product of x with y. I can use the metric of the underlying Euclidean space, GE, or I can calculate the metric of x and y using the metric of the underlying sphere. We don't know the metric of the underlying sphere, but we do know the metric of the underlying Euclidean space. Or in our case, this would be the glome, and this would be R4 in the glome. So if I express x and y in terms of the coordinate basis of R4, I can use this metric to calculate the inner product of x and y. Now, likewise, if I expressed x and y in terms of the coordinate basis of R of the sphere itself, of the glome itself, then I would have to use this metric, which I don't know. But the good news is that regardless of which metric you use, the presumption is the answer is going to be the same, right? X and y has an inner product, and that inner product should be independent of whether or not I use the coordinate system attached to the sphere or the coordinate system attached to the embedding space. And I'm going to use that fact to calculate this metric. Right? I'm going to calculate the metric components here, and I'm going to use that fact to calculate this guy. Because what I would normally do is I would say, okay, I've got x mu partial mu, y nu partial nu in Euclidean space, right? And that's going to equal, it's just going to equal a whole mess of things, right? It's, if I broke it down, it would be x partial x plus y partial y plus z partial z plus w partial w, inner product x partial x plus y partial y plus z partial z plus w partial w. Actually, what if I? That's not good. All of these. I mean, my choice of components was really unfortunate here. This would be vector x x, vector y x y, vector x z component, vector x w component, vector y x component plus vector y y component plus vector y z component plus vector y w component. Okay, that's what that would be. And then, of course, by linearity, what do we end up with? We end up with xx, yx, partial x plus xy, yy, partial y plus xz, yz, partial z, plus xw, yw, partial w. And there are no cross terms because the cross terms are zero because we have that partial nu is delta mu nu for the Euclidean basis, right? That's the Euclidean, right? Euclidean. So we end up with this guy. And so that inner product, right, has to equal the inner product x mu prime partial mu prime y nu prime partial nu prime in the glome metric, right? So now we actually have some trouble because this is going to end up being with my sort of matching the mu primes to phi 1, phi 2, and lambda. It's going to be x phi 1 partial phi 1 plus x phi 2 partial phi 2 plus x lambda partial lambda, and then it's y phi 1 partial phi 1 plus y phi 2 partial phi 2 plus y lambda partial lambda, And this is going to be x phi 1, y phi 1, partial phi 1, partial phi 1. But now we're not sure about the cross terms, right? So it's going to be x phi 1, y phi 2, partial phi 1, partial phi 2. And this, of course, is in the glome coordinates, etc., right? But ultimately, all of this stuff, all of these guys have to be equal. And in the coordinate basis, by the way, we do know that these cross terms will go away also, because that's kind of, they're independent. Well, we really don't know. We really don't know. So we want to make and execute this calculation so we can learn what these guys are. We're after these guys, because these guys, that would be g phi 1, g phi 1, right? Because remember, well, that is g phi 1, because the definition of g alpha beta is the inner product of phi alpha phi beta. That's the definition of what these metric coefficients are. So we're looking to capture and figure out what those guys are. But if that's all we're doing, if we're just trying to calculate what these guys are to get these metric coefficients, right? Well, let's just calculate them. I mean, we know the relationship between phi 1 and the Euclidean basis of the underlying space. We know this relationship here. I can actually plug in this vector here every time I want to use this vector here. And I can do the calculation in Euclidean space on this, and I can get the answer for that. So to demonstrate, we're interested in g phi 1, phi 1. Say I want to know what that is. Well, I know that that's going to be e phi 1 inner product with e phi 1 in the glome basis. But I know what e phi 1 are in the Euclidean basis. Well, that's also, by the way, that's partial phi 1, partial phi 1, right? That's the coordinate basis. Actually, I should write it, you know what, this in the glome basis is going to be this in the Euclidean basis, because when I wrote down these, I wrote them in terms of the Euclidean basis. When I went back here, right, this is written in terms of the Euclidean basis. So when I write it this way, I guess what I'm meaning is I mean the this coordinate basis vector written in terms of the four-dimensional basis system, and I write it this way. So that's what these guys are. So what I'm going to do now is I'm going to make the substitution. I'm going to calculate this in Euclidean space, and I'll get a number, and that number will be the coefficient. Well, I'll get a function probably, and that function will be the bg phi 1 phi 1. So let's just plug it in, right? So here, e phi 1, I remember was r cosine phi 1 partial x plus r, let's see, I don't remember exactly what it was, plus r cosine phi 2 cosine phi 1 plus r cosine phi 2 cosine phi 1 partial y plus r, and let's see, what order do we do it here, r sine lambda cosine phi 1 r, well, let me see, maybe I should just sine cosine phi 1 sine phi 2 r sine lambda cosine phi 1 sine phi 2 partial z, and then plus r cosine lambda cosine phi 1 sine phi 2 partial w, where the only difference between these two is sine versus cosine there. So that vector taking the inner product with itself, right? So I could actually copy this thing. Oops. I could copy this thing. I just cut it. I want to copy it. Copy, paste. Right. So I take it. Here's the comma, right? The comma for the inner product, and then here's the closing bracket of the inner product. And now I write Euclidean here because these are two Euclidean vectors. And this is pretty easy now. Now I take the inner product of this with this using linearity, and knowing that all the cross terms are 0 because the inner product of this with this and this will all be 0. The only ones will survive are the diagonal ones. So the answer is going to be r squared cosine squared phi 1 plus, actually everything's going to have an r squared, so I'm just going to pull that out. And then this will be cosine squared phi 2 cosine squared phi 1. And then these guys go away because they all end up being things like phi y, which equals 1, right? So they're all the diagonal in the Euclidean metric, they all equal 1. So then what do I have? Then I have sine squared lambda, cosine squared phi 1, sine squared phi 2, plus cosine squared lambda, cosine squared phi 1, sine squared phi 2. Okay, so that sum equals g phi 1, phi 1. So on the glome, the first matrix, or the first, I shouldn't say matrix element, the first component of the glome metric is this long expression of squared sines and cosines, which makes, I mean, there's some reason to understand this, right? The surface of the sphere is going to have a much more complicated way of figuring out how to find the distance between points. It's not going to be nearly as simple as the Euclidean metric. It's going to be something else. And clearly you can see it's going to be some complex function of the phi 1s, phi 2s, and lambdas. On the other hand, it's not as complicated as this. I'm just not quite done with my analysis, right? If you look carefully, the sine squared and the cosine squared lambda, this term is the same, cosine squared phi 1, sine squared phi 2. It shows up as a factor for both of these lambda terms, which means I can pull it out, and of course I end up with sine squared lambda plus cosine squared lambda times cosine squared phi 1 sine squared phi 2, and this of course equals 1 by the Pythagorean rule, which leaves me now with what? It leaves me with cosine squared phi 1 plus cosine squared phi 2 cosine squared phi 1 plus cosine squared phi 1 sine squared phi 2. So now I see, oh look, I've got the cosine squared phi 1 as a factor of a cosine squared and a sine squared. So that becomes cosine squared phi 1 plus cosine squared phi 2 plus sine squared phi 2 cosine squared phi 1. Then of course this goes to 1, and then I'm left with, wait a minute, hold on, wait a minute, something's clearly wrong here because I'm ending up with a cosine squared phi 1 plus cosine squared phi 1, and I know that's not the answer. The reason is because here that should have been a sine phi 1. That should have been a sine phi 1, right? If I go back to my definition of E1, I see it's minus r sine phi 1, not cosine phi 1. So that error propagates to here, to sine squared, this cosine squared becomes a sine squared, this becomes a sine squared, and then this ends up being sine squared phi 1 plus cosine squared phi 1, which equals 1. And then, of course, this factor of r propagates too. R squared propagates. So this whole thing gives me g phi 1 equals r r squared. Okay. So it is actually kind of nice and simple for that particular first component. So we can do this for the second component. Right? We can look for g phi 2, which is going to be, the way we calculate that is we go e phi 2 in the Euclidean basis, and that will equal partial phi 2 in the glome basis, right? And that one, let's see, so e phi 2, now I have to go back to here again, and now look at e phi 2. And this time, instead of guessing, what I'm going to do is I'm just going to take it and copy it over, because I made that mistake last time. Whoops. Oh, I don't want that. That was a little too much. Alright, so I guess I'll have to remember. So this is going to be r, and let's see, so let's look at it. It's sine, and then sine and cosine. R sine phi 1, sine phi 2, partial y plus r sine lambda sine phi 1 cosine phi 2 partial z, and then plus r cosine lambda sine phi 1 cosine phi 2 partial w. Because the partial x term was 0. Then I put a comma there. Make sure I got that right. I'm looking here, sine, cosine, sine phi, psi phi. And there's a negative sign that gets introduced up here. I'm wondering if I'm missing a negative sign down here. No, phi 2. So the derivatives of these two signs are just cosines, so I don't get any negative signs except for here where it's cosine phi 2. Okay, so that's good. So then this, I can copy that, and I'm taking it against itself, right? And I guess this is a w. And then what do I end up with? I end up with equals r squared again, and then this is going to be sine squared phi 1, sine squared phi 2 plus sine squared lambda sine squared phi 1 cosine squared phi 2 plus cosine squared lambda sine squared phi 1 cosine squared phi 2, like that, right? And then the same thing happens here with these sines and cosines, so I end up with r squared of sine squared phi 1 sine squared phi 2 plus sine squared phi 2 cosine squared sine squared phi 1 cosine squared phi 2, sine squared phi 1 cosine squared phi 2. And then I can take out a sine squared and cosine squared here, so I end up with an r squared sine squared phi 1. And that's going to equal G phi 2, phi 2. And then I guess we're left with the calculation of G lambda lambda, which is going to equal E lambda, calculated in the Euclidean metric, which is, the point is it's partial lambda in the glome metric. And this guy, now I have to go back again, and I'm looking here at this, it's r cosine lambda, sine phi 1, sine phi 2, so it's all sines, cosine first, sine second, and there's a minus sign. So it'll be r cosine lambda, sine phi 1, sine phi 2, minus r sine lambda, sine phi 1, sine phi 2, partial z, partial w, comma, and then I cut and pasted since we're doing it against itself. I can put it back there and give it the closing parentheses, and this is in the Euclidean metric, and it's going to be r cosine squared lambda, sine phi 1, sine phi 2, r squared, plus, those minus signs go away, right? R squared, sine squared, lambda, sine phi 1, sine phi 2, which is going to, and then of course the sine and the cosine come out because r squared, sine phi 1, sine phi 2, r squared, sine phi 1, sine phi 2, that factors out, leaving cosine squared plus sine squared of lambda. So you end up with r squared, sine phi 1, sine phi 2. And that equals G lambda lambda. Now, I'll leave you guys to prove for yourself that all the cross terms are 0. So all the non-diagonal, all this guy's 0, phi 2, phi 1 is 0. If you can prove that those are 0, I think that's it. And then there's symmetry, right? So I'll let you show that they're all 0. So we have found all of the matrix elements, and therefore we know that G alpha beta in our system is going to be r squared. It's going to be r squared sine phi 1 and r squared, sine phi 1 squared, r squared sine squared phi 1 sine squared phi 2. 0, 0, 0, 0, 0. If you must draw it as a matrix, then it would look like this. But you could also write it down in metric form, which would be r squared d phi 1 squared plus r squared sine squared phi 1 d phi 2 squared plus r squared sine squared phi 1 sine squared phi 2 d lambda squared, which could also be written in the form r squared d phi 1 squared. I'll get rid of the parentheses now. You know the difference between a subscript, superscript, and a squaring, right? Plus sine squared phi 1 times the quantity d phi 2 squared plus sine squared phi 2 d lambda squared, right? And this guy here, right? This guy here is sort of the normal form of this metric. And it looks very much like the standard spherical form of a metric, right? The spherical form of the metric was d theta squared. It was r squared d theta squared plus sine squared theta d phi squared, right? And you can kind of see this is sort of the same, right? This takes the place of phi, and you see you have a sine squared of this of you see that you have the sine squared of like the other angle, right? This is a 0 to pi angle. This is a 0 to pi 2 pi angle. That's the 0 to 2 pi angle. That's a 0 to pi angle. So you have that. What you're missing is this, but of course you don't have a second 0 to pi angle on the regular sphere. The glome, you introduce those things, so it just gets a little more complex. But you can see how this, you can imagine that this is like the most elementary version of something that looks like this, which is a little more elementary than the next dimension, which will have an additional 0 to pi type angle. Anyway, this is the metric on the glome. And the reason I went through this trouble to get the metric on the glome is if you look at the spatial part of this metric, right, that's exactly what you're dealing with. The spatial part of this conformal compactified system, you have two angles that go from 0 to pi. That's c and theta, and there they are. There's c and theta, and then you have one that goes from minus pi to pi, which is what we're calling 0 to 2 pi, and that's this guy. Oh wait a minute, I'm sorry. That's not the right one. There's one that goes from 0 to 2 pi, but I've cut it off here, and that's phi, right? That's what they're calling phi. And this one here is the time variable. Just ignore that for now because we're just looking at the purely spatial Euclidean part. And that's this. And that there is actually a glome. So ultimately what we learned is that in Minkowski space, when we did that whole analysis of Minkowski space, the spatial part of Minkowski space in compactified coordinates is conformal. It's conformal to the Lorentzian glome. And that's kind of why I chose this example, because I want to go through this catalog with some thoroughness. I want you to understand what this is. This is the three-sphere, or the glome, and that part is a time coordinate that's tacked on. And Minkowski space is conformal to that in the sense that the metric of Minkowski space, when you compactify the coordinates the way we did, it's related to this Glomian metric through the simple multiplication by a function. And we haven't talked about conformal coordinates yet, but this is not Minkowski space. This is Minkowski space. The relationship between the two is something called the conformal relationship. And it's interesting that Minkowski space has this conformal relationship to the four-dimensional glome. Okay, so that was what we did. Is we showed we showed how you can take a embedded surface and discover the metric of the embedded surface by utilizing the metric of the embedding space, and in this case it was Euclidean space. The point being that the Euclidean space is simple, we understand its metric very well, and now we've gone through this whole massive process and we learned that the embedding space, its metric is going to be somewhat complex. But you could calculate the length of curves as long as it's in the subspace, right, in the sphere or in the glome, using the metric of the coordinates associated with just the sphere or the glome. And the point is that in general relativity, you don't do this, ironically. In general relativity, we have four-dimensional space, right? But we don't think of four-dimensional space as being embedded in some sort of five-dimensional space. We're going to use only the coordinates within the space itself. It's as though we live on the glome. And our metrics are going to be kind of complicated, right? Our metrics are, not only are they complicated, they're not complicated because we're a space sitting in a higher dimensional space. They're complicated because the metric is a distorted, wacky version of flat space-time because of the Einstein equation. Now, there's this temptation to think, well, maybe there's a simpler metric in a higher dimensional space that could make everything easy. But we don't do that, and we don't even try to do that, and it's not clear that there is, because we're not a smooth, nice glome anyway, right? We're some wacky shaped space-time. But we're stuck with these hard metrics but in our space-time, but we're looking at it from inside our own space-time. We're not referring it as though we're embedded in some higher dimensional space. So we're like, it's in sort of by analogy, it's like we're stuck on the glome, and we have to live with this metric here, this complicated metric, to figure out how far apart things are. Okay, so anyway, so now we've gotten a little facility with metrics, and next time we get together, we're going to start attacking this problem here, this question. We're going to start discovering how the connection is related to the metric, and that's actually quite a long journey.